All right, I'm starting the stream right now. So this way, it synchronizes with, the start time of 9 o'clock. If you guys, jot down the time of a particular topic, it will be a pretty even offset, easy to compute, how far into the video you need to go. All right, so I am starting now. All right, so a few things. I just, reminded myself to start OBS and start streaming, and that part is done, checked. All right, I like that. Check. We do have it in exam one, which according to the syllabus is about 1/3 through the semester. So I scheduled that on September 29th, which is week 6. This is the end of week 4. Next week is week 5, and then that's going to be week 6. The topic included will include what we will be talking about today. And then on I guess it will be on next Thursday. So on next Thursday, I'll give you a practice exam, but I will give you the practice exam question, like even today. And so you guys can kind of spend the weekend to try to kind of figure things out. It may be difficult at first, so I will basically go over that sometime next week to give you guys some clues, as to how to get, started, how to think about it, how to problem solve, that sort of stuff. All right, so the exam itself is going to be in person and it's going to be paper based. In other words, there won't be any electronics other than a calculator. You can use a graphing calculator if you want to. I think that's going to be an overkill because the topics that we have talked about so far mostly are just multiplication, addition, subtraction, that sort of stuff. You really do not need a complicated calculator. But since most of you are taking calculus or have taken calculus, you probably have a nice graphing calculator. Hey, that's fine too if you want to use your graphing calculator. If not, any calculator from the Dollar Tree would work. Trust me. All right. So with that said, are there any questions? I will tell you more about the exam as I have started to write a document because every semester I have to go through this, and I just decided to consolidate all the discussion into a single document that talks about the exam policies. So this way people can know what they can expect during the exam. Can we ask questions during the exam? The answer is yes. Okay. The only thing you have to think about is how am I going to answer those questions? Because I have had people, taking their exam to me during the exam and ask, Tech, do you think my answer is right? Well, I do answer those questions. The answer was, I cannot tell you. All right, so I do want to set up the expectation, just so that you don't end up wasting your time coming all the way up here to ask me a question, and then I cannot tell you, what you want me to tell you. So I will share this document with you when it is ready. Right now it is not quite done yet, so I'm still working on it. All right, so getting back to what we are going to talk about today, we are done talking about signed versus unsigned. The lab from Tuesday hopefully will help you, basically consolidate your understanding of, how we represent values that are negative, but only using zeros and ones. Okay, so two's complement is basically a mechanism to perform what we otherwise know as arithmetic negation. So that's basically where we are at this point. So what we're going to talk about today, let me go to that particular slide. It is binary comparison. In other words, if we need to compare two values and find out which one is less than, whether the first one is less than the second one, how do we do it? Okay, so that's going to be the focus of today, both in the lecture and also in the lab. Now, you guys have already noticed, okay, the lab is usually related to the lecture. So that means, if you're not understanding the concepts during the lecture, make sure that you ask those questions, okay? Or you can chew on it a little bit first, but if you cannot figure it out, then go ahead and ask those questions, because otherwise the lab can be more challenging than they are supposed to be. All right, so with that said, I'm just checking on whether the other student is online, and unfortunately, the student is not online right now, but that's okay. It is not my responsibility to make sure that people attend the class. So what we'll start off with is we only need to know whether a number or a value is less than another value or not. So some people may be asking, well, but what about all of the other comparisons? What about greater than? Greater than is easy. Just flip the operands, and then now you have greater than. Another one that's easy, once we have greater than, is not equal to. So how do we know whether A is not B? Well, if A is less than B, or if A is greater than B, then A and B are not the same, right? Equal to is also easy because once we know how to tell whether A and B are different, put a negation in front of it. Now it is equal to. Less than or equal to. If A is less than or equal to B, A is greater than B. Or I should say, it is not the case that A is greater than B. Okay, there's a negation in front of it. But nonetheless, we can translate all of the other comparison operators into just less than combined with some logical operators. So that is why we really only need to know whether A is less than B. So now we go back to interpreted value. This is a revisit of something that we have seen before, but in a slightly different format. So let me go ahead and explain, what these notations are trying to tell you. So we have a VU of XM. So V is value, U is unsigned, X is a bit pattern that can have many, many digits, but M is basically saying we only want to interpret up to M digits. So what that is implying is X may have more than M digits, but we only choose to interpret the first or the least significant M digits. So is that okay? Does everybody understand the context or the meaning of VU of XM? We good? Okay, so this is something that you might want to write down even though it is in the notes. Is V is the value, U is unsigned interpretation, X is the bit pattern, and then M is specifying only interpret up to M digits from digit 0. So the expansion is something that we have seen already, and I remember the actual module number, which is kind of disturbing because it is module 0282 when we talked about base conversion. So this particular sigma notation should look familiar because even though it's not exactly the same as last time, because last time it went from negative infinity, I goes from negative infinity to positive infinity. This time it is limited because we only want to interpret up to M digits, starting with digit 0. So are there any questions about this particular definition? Okay, no questions. The int interpretation is a little bit more tricky. Congruent modulo 2 to the power of m helps to understand how a bit pattern can represent different values, blah, 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 blah. Okay, but in the end, okay, I'm just fast forwarding and skipping to the end here. So in the end, we have Vs. Can anyone kind of guess what the S is representing? Signed. Very good. Yep, you guys are correct too. So it is the value interpreted signed of the bit pattern of X. Remember, X has no inherent value. X is really just a bunch of zeros and ones arranged in a certain way. That's what X is. So the interpretation is based on how this function is defined. And once again, we only want to interpret up to the first or the least significant M digits, starting with digit 0. So the way I express that is a little bit strange. The first part seems to be the same as the unsigned interpretation. But if you look closer, I only goes from 0 to m minus 2, not m minus 1. M minus 1 is the most significant digit out of the first or the least significant m digits. This one only goes up to m minus 2. So what about the most significant digit? The most significant digit is right here. It is actually subtracted. So x subscript m minus 1 times 2 to the power of m minus 1 that amount is actually subtracted. That is a sign bit, okay? So the sign bit, as it turns out, can also be interpreted as, are we supposed to subtract a big chunk out of the summation of the other bits, okay? So it's time to show you a few examples, right? Because this looks pretty abstract. So let's go for some examples, and let's see, I need to go to Zernal. Well, Zerno will work. I think Joplin works better because I can type. So I changed my mind. Sorry, I want to use Joplin instead of Zerno. All right. So I will go ahead and show you a few examples, and this is already done. So let's look at V subscript U of the bit pattern of 100101 in base 2. And we want to interpret the first 4 digits. Okay, so what is that going to be? Well, that's going to be the summation of the least significant 4 digits. So we have 1, we have no 2, we have 1, 4, and we have no 8. So that turns out to be 5 in this case. Do we have any questions about this? No questions? Okay. All right, and I'll give you an example of VS. So VS, which is value interpreted signed, and we're going to pick up the same bit pattern, 100101 in base 2, and this time we'll pick up every single digit, which means we're going to specify 6 digits in this case. So we'll try to figure out what's going on here. So remember, it's going to, in this case, it will basically sum up the least significant 5 bits, okay? The digit itself multiplied by 2 to the power of the position of the digit. So it would look about the same as the one before because we still have the 1, we still have the 4, but then this time we have to subtract the most significant digit, which is this digit here, times 2 to the power of the position of that particular digit. That turns out to be position 5 or digit 5. So now we have to subtract 2 to the power of 5. So that becomes basically 5 minus what is 2 to the power of 5? 32. And that turns out if you do the subtraction, it is 27, I think, negative 27. There we go. So do we have any questions about the 2 examples of using the unsigned interpretation of a bit pattern and the signed interpretation of a bit pattern? Yes?
So can you go over the first one? How?
The VU or the VS?
The VU.
The VU? So the VU says only interpret the least significant 4 bits. So that is why we only pay attention to these 4 digits, because the other 2 digits, the most significant 2 digits, are not within the range of what we're interested in. So you might be asking, but why do we need to specify a boundary of only interpret up to this many digits? Well, that has to do with a proof that I need to do later on. So we are really just looking at a notation that allows me to express certain things in the proof in a way that's just kind of more abbreviated. But for those of you who are looking at the second example, which is the signed interpretation, you go like, but Tech, I'm not really sure about that. Okay, can you show me the signed interpretation of 100101 in base 2 is supposed to be negative 27? Can we use something that you learned on Tuesday? What do you think something from Tuesday can be used in this case to double check that negative 27 is indeed the signed value represented by the same bit pattern? 2's complement, very good. Okay, so let's do that right now. So I'm going to start with the next line here. So with 2's complement, I'm going to use something like this. Okay, so we'll go for, this is 100101 in base 2. All right. There we go. All right, so this looks really silly, right? I have a bit pattern and I have a double arithmetic negation here. But that's because, double arithmetic negation cancels itself, so I should still get the same value back. Because my intention is to find out what exactly is 1000101. What is it representing? So I don't want to change that. The next thing I do is to say, but one of the arithmetic negation can be done using 2's complement. So this is where it starts to make a difference. So let's see. I think I can do this just to make it look nicer. So now we have your C2 applied to the same bit pattern, which is 100101 in base 2. Is that part okay? Does everybody understand why I can take out one of the arithmetic negation and replace it with 2's complement? We good? Okay. And then we just carry out the 2's complement. 2's complement is translated to 1's complement. So we call it C1 of the same bit pattern, which is 100101 in base 2, and then the whole thing plus 1. That's basically the definition of C2 in terms of your C1. 2's complement is 1's complement plus 1. 1's complement is just flipping all the zeros and ones. So now we end up with 0, 1, 1, 0, 1, 0 in base 2, and then the whole thing plus 1. And that turns out to be a pretty easy addition because we now have 0, 1, 1, 0, 1, 1 in base 2. All right, so are we still doing okay at this point? Are there any questions? No questions? So now the question is, oh, I forgot one thing. I forgot to carry that overall arithmetic negation throughout this operation. So please forgive my negligence in this case, because I forgot there's a negative in front of everything, because that is important. Okay. All right. So now that I got that added and I'm out of space, so now the question is, what exactly is 0, 1, 1, 0, 1, 1 in base 2? Well, we just have to count, where, which power of 2 is present. Okay. 1 is present, 2 is present, 4 is not present, 8 is present, 16 is present, 32 is not present. So now we have the 8 plus 2, which is a 10, and then the 1 plus the 16 is 17. 10 plus 17 is 27, indeed. So this is a different way to try to figure out what signed value is being represented by a bit pattern, and it arrives to exactly the same value. So is it a proof that the techniques are correct? No, it is not a proof, but it is a validation that at least in this specific example that it works. Are we good so far? All right. So this is a small exercise here that I'm doing to try to help you make connections between what we are learning today and what you have learned already, because that is the most important part about taking a class or learning anything, is to make all of those connections. Nothing is truly standalone when you're studying, any type of STEM field. All right, so with that said and done, the next thing we're going to do is to go back to my slide and maximize it. There we go. And now we are ready to talk about less than, unsigned. In other words, if I give you 2-bit patterns and I'm asking you whether the value represented by the first bit pattern is less than the unsigned value represented by the second bit pattern, you just have to tell me true or false. How do we do that? So you look at this particular section and go like, oh my goodness, there's so much math stuff in it, right? Well, the math stuff is only here to convince myself, okay, that the conclusion is correct. The overall borrow is the key. Okay, so let me just jump to the conclusion first. In a binary subtraction of 2 m-bit patterns, x minus y, so x is an m-bit pattern, y is also an m-bit pattern, tm equals to 1. What is tm again? Do you guys remember the notation? Once again, we are trying to make connections with things that we have learned already. What is Tm? What do I use Tm to represent? Okay, I'll give you a hint. Binary subtraction. So in a binary subtraction, what is T? The borrows. Very good. So Tm is representing the borrow of position M, which is the overall borrow when you have an m-bit number subtracted by another m-bit binary number. All right. So what this is saying is if the overall borrow between the subtraction of x and y is 1, that can only happen if and only if vu of xm is less than vu of ym, assuming t of 0 is 0. Okay, so is that making any connections in your mind? Because now we are starting to introduce the terms that we introduced today, which is vu, and we are now connecting all of that stuff back to binary subtraction, specifically the overall borrow bit. So do you understand the statement? Are there any questions about the statement itself? Not so much why it works, but just what it is trying to say. No questions? All right. So if there are no questions, we'll go through a few examples just to show whether this works or not. Okay, so we'll go to, I think for this, I'm going to use Zerno because your tables can be done in Joplin, but it's just not as intuitive as doing it in Zerno. So I'm going to use Zerno for this. All right. So we'll go through, like a few, 4-bit subtractions, and these subtractions will also be reused later on, for a different reason. So the first one is 0, 0, 0, 0 minus 0, 0, 0, 1. In essence, we are comparing 0, 0, 0, 0 and 0, 0, 0, 1. And we're trying to determine whether 0 is the first one, which is x, is less than y or not. So I'm keeping the same nomenclature. This is x, this is y. X is also known as the minuend in a subtraction, and y is also known as the subtrahend in a subtraction. You do need to know those terms because of the lab would refer to those terms. So you might want to kind of make some notes. X is also known as the minuend, M-I-N-U-E-N-D, and then y is known as the subtrahend, which is S-U-B-T-R-A-H-E-N-D. Anyway, the next one is Q, the next one is T, and then the last one is D. And the funny thing is we don't really care about D that much because all we need to know is whether x is less than y. So we're going to carry out this. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. All right. So can someone tell me in this particular subtraction, what is m? Remember, m is representing the width of the integer. So what is m in this case? Is it 4 or is it 5? It's 4. That is correct. Okay, so m is 4 in this case. And which one is T4? You can describe the position. Which one is T4? Which bit is T4? Obviously, it has to be on the row of T, right? So on the row of T, we got 5, digits. Which one? Sorry? The leftmost one or the rightmost one? The leftmost one. That is correct. Okay? So the leftmost one is this one over here, and it is telling us that x is less than y. You guys go like, wow, that's not exactly exciting. Because in this case, v u x of 4 is just 0. V u x, oops, y of 4 is 1. 0 is less than 1 is true. Wow, okay, so the borrow bit tells us the right answer. Okay, very good. Let's try something else. Okay, this time we are going to try 0, 0, 0, 0 minus 1, 1, 1, 1. Okay, so we'll try to find out what's going to happen this time. We got x, we got y, we got q, t, and d. There we go. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 0 minus 1 is a 1 with a borrow of 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow of 1. 1 minus 1 is a 0. 0 minus 1 is a 1. 1 minus 1, with a borrow of 1. 1 minus 1 is 0. So once again, this is telling us that x is indeed less than y because t4 is a 1. Does it make sense? Well, let's check out. VU of x using only 4 bits is a 0 because 0, 0, 0, 0 is probably really just 0. How about VU y 4? That is 1 plus 2 plus 4 plus 8, which is 15. So we say 0 is less than 15. Yeah, we know that for sure. Yep.
So you said the t, like the leftmost digit of t, is 1?
Yeah, if that is what, if an, okay, T4 or the most significant borrow bit is a 1, if and only if the unsigned interpretation of x is less than the unsigned interpretation of y. That is the statement.
If and only.
If and only if, which is very important because if you say if, you're missing some cases. If you say only if, you're missing some other cases. So you have to say if and only if. Mm-hmm. All right, so these two kind of checks out, right? Let's see. I'm trying to give you a few more cases. Oh, I got a really good one here. So I'm gonna scroll. Oops, it scrolls too much. So let's try 1, 0, 0, 0 minus 0, 0, 0, 1. Okay. This one is super easy, okay? So I'm not even going to bother to kind of spell out the actual subtraction. Okay? So based on the result of this binary subtraction, what do we know about x and how does it relate to y? Is VU x4 less than VU y4? The answer is no, okay? But why is that the case? Does it make sense to you? VU x4 in this case is what? What is 1, 0, 0, 0 in base 2? Unsigned interpretation. It's 8, okay? And what about y? That's just 1, okay. So 8 is less than 1 is false. Okay, wow, okay, so it seems to work just fine, right? Let's see, I think I can give you one more test case. And I have to think about which one I want to use because I'm going to reuse these cases for signed subtraction as well later on. So I need to figure out one that is also going to illustrate something important when we deal with signed interpretations. So give me a moment here, to try to think of one case. Oh, I got one. So the last one that I will talk about, just as an example, is 0, 1, 1, 1 minus 1, 1, 1, 1. Actually, it's 1110. Okay, there we go. All right, so I'm just going to go through this rather quickly. Um, it's a 1 here, there's a 1 here, there's a 0 here. Um, 0, 0, 0, 0, 0, 0, 1, 1, and a 1. Okay, so just from looking at the bits that I have figured out at this point, is the unsigned interpretation of 0, 1, 1, 1 less than the unsigned interpretation of 1, 1, 1, 0? Yeah, because the overall borrow bit is a 0, is a 1 in this case. So that's telling us x is less than y when we interpret the bit patterns as unsigned. But does it make sense? VU x4 is 7 in this case because it's just 1 plus 2 plus 4. And then VU y4 is 14 because we have 2 plus 4 plus 8 is 14. So in this case, we say 7 is less than 14. Oh yeah, I mean, that's definitely true. So are we starting to understand, what I mean when I said if and only if the overall borrow is a 1, x is less than y. Okay? You go like, but that seems pretty easy. Why in the notes we have a whole bunch of gibberish, a lot of math symbols and whatnot? Because that is my proof. This is a mathematical proof of why it works. Now, do you have to understand that part? The answer is no. Then the next question that some of you might have is, but why did you put it there if we don't need to understand it? Because some of you may want to get into a habit of at least looking into a proof and go like, okay, so now we know for sure that this works. It's not just for the few examples that I show you that it works. We know the approach works. I can prove that it works. Okay? Well, that said, if you have already taken CISP 440, you should be able to follow through the proof itself. Now, do you want to do it? Now, that's a whole separate question, right? Because I know you guys have other classes to worry about and stuff like that. So following a proof like this may not be something that you prefer to do. All right, so that's for unsigned comparison. How do we know x is less than y when they are interpreted unsigned? So signed is a little bit more complex. Unlike unsigned, where the actual difference of x and y cannot be its own value when VUXM is less than VUYM, signed int can represent the actual difference of x minus y. So let me explain what I mean by that. Because when you have unsigned subtraction or unsigned interpretation, if x is less than y, if you just look at the difference, which is only 4-bit wide in this case, it's always going to be non-negative, which doesn't make sense, right? Because you have to take into consideration the borrow bit. The borrow bit is saying, wait, hold on a second here, okay? If the borrow bit is a 1 in a 4-bit subtraction, you are owing 16. Okay, so you have to look at the actual unsigned value of the difference, but remember to subtract 16 if and only if the borrow bit, the overall borrow, is a 1. So that is how we represent something that is quote unquote negative because of the borrow. Okay, the borrow says, hey, you still owe 16 in this case. So this entire discussion, kind of ends with two things. Okay, so it ends with the conclusion here of L1. Okay, I'm not sure how to move that up because people in the back may not be able to see this. So I might need to unzoom and change the size of